Alright, here we have our physics projects, the pencast of me shooting a basketball. And before I start, I'd like to explain some key measurements. From the hoop to the three-point line is about 6.01 meters, and the basket is about 10 feet tall, but we chose the top of the backboard, which is 13 feet, which is about 3.95 meters. And we chose this because as the ball leaves my hand and reaches the highest peak, it's at about 3.95 meters. So that's why we chose that. And the first thing we analyzed was Newton's laws as I go ahead and play it here. And as I'm holding the ball, Helen pointed out that the ball is, I'm applying a force to the ball, and the ball is also applying an equal amount of force back on me, and which relates to Newton's third law, which says for every force applied to an object, there's an equal but opposite direction force acting on a different object. Newton's first law is also applied because when I release the ball, it'll continue to stay at constant speed unless acted on by a force or another object like the backboard or net for this example. And when I looked at this video, I saw that I use energy to bring the ball down and bring it back up and as I jump. And there's also work done on the ball when I release it from my hands. I put backspin on the ball so it travels like a projectile. And right here is when I'm at the peak and I'm about to release. And when I said before it travels like a projectile, and Lauren pointed this key fact that it travels like a projectile motion, but I'll get back to that. The average amount the ball spins in an average jump shot is about 8 rotations, which goes back to when we learned about rotations. The work done on the ball carries the basketball to the hoop and through the net. And going back to Lauren's point, the time at which the ball travels toward the basket in the x direction and goes up to its highest peak is equal to one another, and the highest peak is right here. As you can see, it's equal with the top of the backboard. What affects the time of flight is gravity, air resistance, which is very minimal in this case, the angle measure at which the ball leaves my hand, the speed of the object, and the mass of the object. In addition, in this example, the acceleration stays at a constant 9.8 meters per second when it goes up and when it goes down because of gravity. And as I play it, you can see that the ball right here in our graph reaches at a peak right around here, and this is all when I bring it up as I release. And we figured out that this was all invalid data right here because it stops tracking as after it goes through the net. And when we were talking about 2D forces, Haley pointed out the ball has force of gravity acting upon it throughout the video, and also that I apply a force to the ball so it travels to the basketball hoop, and once the ball gets to the basket, it experiences friction from the net as you saw as the ball went through, and the ball accelerates at a 9.8 meters per second squared as it falls to the ground. And we figured out that our video had no velocity because the basketball experiences no velocity throughout, so it stays at a very constant 0. And thank you for watching our video.